In the previous video, we learned about the Mulliken symbols for one-dimensional functions. In this video, we will cover two- and three-dimensional functions. As we can see, the two-dimensional functions are termed as E, such as EG and EU, and the three-dimensional functions are termed as T, for example, T1G, T2G, T1U and T2U. So, first, we will discuss the meaning of two- and three-dimensional functions. Then we will see the meaning of each associated term. As we know, the character of the identity element, E, decides the dimension of a function. Here is the character table for the octahedral point group. If you see the rows, under EG and EU, the character of identity element, E, is found to be 2. Whereas, the character of E in T1G, T2G, T1U, and T2U is 3. Before moving forward, it is important to notify that the term E, representing the identity element, is not same as the term representing the two-dimensional Mulliken symbol E. Both are completely different. The question now is how the character of the identity element E is decided. To understand this, it is important to understand the meaning of closed function and mixed functions in group theory. In molecular symmetry, functions are grouped based on how they transform under the symmetry operations of a point group. If a symmetry operation changes one function into another function within the same set, the functions are said to mix. The same set means a chosen collection of functions that we are testing to see whether they stay together under all symmetry operations of the point group. For example, in octahedral point group, if we want to test the behavior of dxy, dz, and dzx, then we will consider it as a set. Now, we will check if there is any operation that can replace the three orbitals with each other or not. If it is there, then we can say these three functions are mixed. In octahedral point group, if we operate C3 axis, which is along the body diagonals of the cube, it will transform these functions like dxy to dYz, dYz to dxz, and dxz to dxy. You can do the task at your own to verify this. Since C3 can transform all these three orbitals into each other, these functions are called mixed functions under octahedral point group. Other symmetry elements may or may not transform all these three orbitals into each other. For example, C4 axis transforms only dYz to dxz. But with C4 the dxy remains dxy with a change in sign. So, among all operations of the point group, if there is at least one operation that can transform the chosen functions into each other, then we will say these functions are mixed under that point group. Now coming to closed set. When every symmetry operation of the point group transforms the functions only into each other and never into a new function outside the set is called closed. For example, if you apply all the symmetry operations of the octahedral point group on the dxy, dYz, and dzx, they will never transform to dx square minus y square or dz square. These elements will only transform within their own set, like dxy to dYz to dzx to dxy. So this is a closed set in octahedral point group. Similarly, we can group dx square minus y square or dz square in octahedral system. Here also, only C3 axis performs the task. It is important to note that the particular grouping of functions will change if we change the point group. Such closed and mixing functions together form a multidimensional irreducible representation. In this context, If a function always transforms only into itself and never mixes with other functions under all the symmetry elements of the point group, it belongs to a one-dimensional irreducible representation.